Welcome back. In this video lecture, we will look at the electrical double layer interaction. Okay. So far we have looked at the van der Waals force of interaction, okay, between two macroscopic objects. Uh, Now in this video lecture, we will look at the force due to electrical double layer or electrostatic force of interaction. Okay, so this electrostatic force of interaction is purely coming from the Coulombic interaction between two charged system. Okay, if two oppositely charged systems interact, there will be electrostatic attraction. If two like charged systems interact, there will be electrostatic repulsion. Okay, we will look at them in detail. Let's begin. Right. So as we described before we begin, let us first understand the van der Waals force constant. Okay, from where we left. Right. Right. So it is very important that you should know that the beta, which is the van der Waals force constant, carries unit with it, right? So there is unit, right? So which means that the beta uh, is nothing but the joule meter power 6, right? So eventually you will have the unit of the interaction potential energy as joule. Okay, so because this beta carries with it three distinct terms. Okay, so depending on the situation, uh, sometime all three terms exist, right? Sometime one or two terms exist, right? But it is very important to check the unit consistency always, right? So sometime you may deal with uh, depending on the situation, you might deal with all three also. So it is very important that you need to look at the consistency of the unit, verify the unit first, right, before computing the pairwise interaction potential energy. All right. So in this case, we have got three terms within this bracket. One is d by key sum and London dispersion force. So it is important for us to check that each term will have a unit of joule meter power 6, right? Then ultimately one would have the energy, total energy as joule. Okay. So I have also listed the uh, important microscopic parameters like polarizability, which is alpha, dipole moment, okay, and vacuum permittivity. Okay, the unit of all are also given here. Now let's first take the d by, okay, interaction, right? So the unit of this d by must be joule meter power 6. Let's first analyze that. The rest of the terms can be done by yourself as an exercise. Okay. Let's say we have the in this case we have alpha, which is nothing but Coulomb square meter square joule power minus 1. Okay, that's what given here. And we have dipole moment, which is mu, right, which is Coulomb and multiplied by meter. But since we have mu square, it will be also Coulomb square meter square. So eventually you will have Coulomb per 4, right, power 4 and meter power 4. So this will be your unit, right? Remember you have one in the denominator as well, which is vacuum permittivity. So vacuum permittivity is usually defined as Faraday, right? I think F by M, right? So it's given here. So it is also nothing but Coulomb per volt, right? So F is also nothing but Coulomb per volt. Here it is, F is a Faraday's constant, right? So Coulomb per volt. Now you can also notice that Coulomb is defined as joule per unit volt. Okay. So you can also write this equation in terms of coulomb. That is, let's say if you replace volt, right, with the coulomb and joule, you will have coulomb square, okay, joule per minus 1 and meter per minus 1. So if I substitute over here, because we have got E naught square, this will be coulomb per 4, joule per minus 2 and meter per minus 2. Okay. So in this case, coulomb unit will not survive. Okay, both will get cancelled with each other, and you will have so this will be joule and meter per 6, right. So this is, I think the unit consistency is verified for the case of Debye. You can verify yourself for the case of Keesom and London. Okay, right. So now let us look at before going into the details of the electrical double layer interaction, let us look at some important fundamentals behind the Coulomb's law or Coulombic interaction, electrostatic force, right. So we will understand what is electric charge, electrostatic force and Coulomb's law in this slide, right. So let's say whenever you deal with, right, say whenever there is charge systems, right. Okay, there will be electrostatic force, right. So um, let's say we have a subatomic particle, okay, and subatomic particle will have electrons and protons in it. Okay, depending on the number of electron and the number of the protons. So one would get the charge, the subatomic particle we gain negative charge or positive charge, right. Okay. Now the same thing you can also extend it for two macroscopic objects. Okay, it can be negatively charged macroscopic object or positively charged macroscopic object. Okay, so whenever there is a charge system, okay, the electric field, okay, will emanate from the charge system, and that electric field will interfere with the other charge system, right. So due to which the electric force will be created. So that is what exactly we have shown in the schematic, right. Right. So when such electric force is created, depending on whether two charge system is like, whether both are negatively charged or positively charged, you will have electrostatic repulsion or electrostatic attraction. So what governs this force, electrostatic force, right. That is nothing but the Coulomb's law. Okay. So whenever there is a 2-point charge, okay, let's say the magnitude of the point charge is q1 and q2, okay, and they are kept at a distance of r. It is nothing. The Coulomb's law says that the force, that is electric force here, okay, or the force acting between this point charge will be proportional to the product of the magnitude of the charge, which is q1, q2 in this case. Q1 and Q2, they may be same or they may be different, okay, and it is also inversely proportional to the square of the distance, which is r square. So this square of the distance, okay, uh, you know uh, up to which these point charges are kept, right, with up to which these point charges are interacting with each other. Okay, so that is what exactly we have given here. And the proportionality constant is nothing but 1 by 4 pi E naught. This E naught is nothing but vacuum permittivity. Okay, this is nothing but vacuum permittivity. When I say vacuum permittivity, which means that there is no medium exists. So you just keep this charge system in the vacuum as it is, and how the the interaction takes place. That is exactly you study. In such case, you will use this proportionality constant, that is nothing but 1 by 4 pi E naught. But sometime you will keep this or you will study this systems, right, in a medium, okay, which might contain some electrolyte and all that. So, in such case, how do we deal with? In such case, there is something called relative permittivity, which is nothing but Em by E naught. Okay, Em is the permittivity of the medium, E naught is the vacuum permittivity. So, see, it is difficult to always describe in a different parameter, right. For example, whenever you define a Coulomb's law, you cannot say for vacuum permittivity this is the equation, for medium, for the case where there is medium is considered, the Coulomb's law will be different, right. You cannot have two different equation or multiple equations. So, to generalize this equation, what it has been proposed was, you can actually multiply this E naught with the ER. Okay. Remember, ER has got no unit because it is a ratio between EM and E naught, correct, right. This has no unit. Now, let us say if you are dealing with medium instead of vacuum, what you will be getting finally is the EM itself, because E naught will cancel with each other, you will have EM itself, okay, right. So, or if you are dealing with only vacuum, ER is 1. For vacuum permittivity, ER is 1. In that case, you will have this equation as it is intact, this equation will be intact. So, irrespective of whether you are dealing with vacuum or whether you are dealing with medium, you need not worry. So, you can always use this generalized equation, which is nothing but 1 by 4 pi E naught ER. So, the proportionality constant, the generalized proportionality constant will be 1 by 4 pi E naught ER. Whether you deal with a medium or whether you deal with a vacuum, it takes care of it itself, right. So, in that case, so for water you will be using the instead of E naught alone, you will be using E naught into ER, okay, right. So, this equation, if you look at, this is in analogous to the the gravitational Newton's force, right, gravitational force. Here if you look at, this is also proportional to the masses, right, mass of the two objects, which is m1 m2, and it is also inversely proportional to the square of the distance, right. So, something like this, the Coulomb's law is also described something in a similar fashion, whereas here the proportionality constant will be 1 by 4 pi E naught ER, whereas here the proportionality constant is the gravitational constant, okay. But the unit of these two equation is Newton, because we are talking about the force, the unit of this will be Newton. You can also verify this, this Q1 Q2 will be Coulomb square divided by R will be meter square. So, this is nothing but, so we are just trying to understand, verify the unit. So, this will be Coulomb square by meter square into the E naught. So, you have in denominator, ER has no unit, E naught will be, as you know already, we have just now seen, which is nothing but Coulomb by volt into meter, right. Okay, so, it will be volt meter by Coulomb, because it is 1 by E naught, okay. So, you can say that this is nothing but multiply by volt meter by Coulomb. So, you can say that Coulomb is can be cancelled out, meter can cancel out, can be cancelled out. So, you will have Coulomb on the numerator. So, Coulomb into volt divided by meter will be there. Coulomb is also nothing but joule per volt, right. So, joule per volt, volt by meter. So, volt cancels out. Joule is nothing but Newton meter. So, you will finally have Newton. So, you can see for yourself that the unit of this will be simply Newton, okay, right. So, now we will move on to what is known as electrical double layer interaction or potential. So whenever you deal with electrolyte medium, okay, let's say you have the a container where you have the electrolyte medium. Let's say you have salt like NaCl salt, like you have Na plus Cl minus, Na plus Cl minus, like that. Entire solution will be distributed with this counterions and coions of salt. Now now the question is, the what is the charge of the entire solution? That will be neutral, because Na and Cl will be distributed such a way that the electron neutrality condition is achieved, which means that the charge of the solution will be always neutral. Okay. Now this is one scenario. Let's say in this case, in this medium, okay, containing counterions, coions in the solution, let's say I introduce another system, solid system, which is charged, which is not neutral but charged, which is negatively charged. Okay. Whenever you introduce the negatively charged system, it actually disturbs the electron neutrality, right? So suddenly what will happen? So there will be a change in the ion density near the surface, whereas far away from the surface there will be no change. So this far away from the surface, uh, the electron neutrality is naturally attained, so there will not be any change. But near the surface, there will be change in the distribution of the ion density. Okay, so why is it happening? Because whenever you suddenly introduce the charge system into the electrolyte medium, there will be counterions will because it is negatively charged. This system, the solid system is negatively charged. You can expect the binding, right, counterion binding on the surface of the charge. I mean charged system. For example, the counterions can bind the surface in a three possible way. It can bind the surface, or it can hold the counterions. For example, you will have a strongly bound counterion, okay, or weakly bound counterion, or diffuse counterions. Okay. So this diffuse counterions are held by the electrostatic attraction, whereas this is actually strongly bound by the electrostatic attraction, whereas this one weakly absorbed, weakly bound counterion is attached to the surface by physis option, which is weakly bound. Okay, so in this way you can expect that there will be change in the ion density across this surface, right? Potential variation will be there. Again, so again, if I consider these two as two bulk phases, let's say this is one bulk phase, solid is one bulk phase, and the medium, liquid medium is another bulk phase. If I separate these two bulk phases, right, from this, then you can see that both this bulk phase carry equal and opposite charge. Okay, that is because of the electroneutrality condition. Okay, so uh, so this process is called electrical double layer, and interaction based on this electrical double layer is called electrical double layer interaction. Okay, let's say you got a medium where you have two charges of system, okay, in the medium. So this will have electrical double layer, right, and this will have electrical double layer. So when both interact with each other, there will be electrical double layer interaction, right. So in a nutshell, electrical double layer means when ions are present in the medium, okay, and uh, and uh, uh, and suddenly when charge interface is introduced into the medium, there will be variation in the ion density near the interface, right. Okay, and the profile of that will vary something like this, will will exist. The profile will be something like this. Okay, right. That is exactly what we call it as a electrical double layer. So this electrical double layer will be something like, whenever you separate these two bulk phases, they will carry equal and opposite charges in it. right, such that the electroneutrality condition is achieved. Okay. So here I have listed various models for double layer interaction. As you can see, there are three models: Helmholtz model, GUI-Chapman model, and GUI-Chapman Stern model. Okay, we will look at them one by one in detail as we move along. So let us first consider the Helmholtz model, which is nothing but a capacitor model proposed by Helmholtz, um, right? And in this model, the model considers the uh, parallel plate assumption, which means that let's say you have the charged interface, right? You have a charged interface, and you introduce this charged interface into the medium, electrolyte medium. You have negative charge, right? And there will be counter ions, right? There will be counter ions, there will be three types of counter ion. One is strongly bound, weakly bound, and diffuse counter ion. Okay, and Helmholtz consider only the strongly bound counter ions, which means that if you take out this counter ion phase and the solid rigid phase into two separate plate, both will have equal and opposite charge, right? So that means both will carry equal and opposite charge. In such case, the distribution of the potential, the variation of the potential will be linear. So that is exactly what we have shown in the schematic. Okay, that is exactly what we have shown in the schematic. So which means that if you separate this the entity, that is the solid surface, and the counter ion, if you assume that counter ion is also a rigid layer, and then if you separate them into two, you will have both uh, both will be carrying equal and opposite charge. The distribution of potential in such case will be linear, right? So this model is this model based on capacitor model is nothing but Helmholtz model. So here our starting point, so our point of departure will be, we want to see how this potential variation is linear. So we know that our point of departure will be Coulombic force, right? Right. This comes from the Coulombic law itself, Coulomb's law itself, which means that this is nothing but 1 by 4 pi epsilon naught and epsilon r into q1 q2 by r square. So this is exactly what we know, Coulombic force, right? But we are not just interested in the Coulombic force, but we are interested in the potential variation. So we want to determine what is the electrochemical, or we want to know what is the variation of potential across the in the vicinity of the interface. Okay, so for that we want explicitly the potential variation. So we know that electric field can also be defined by Fc by Q, can also be defined as Fc by Q. So if you just look at this equation, Fc by Q is nothing but volt per meter, which is nothing but electric field, okay, volt per unit length. So you know that Fc can be expressed, how it is coming, Fc can be expressed as Newton itself, and Q meaning Coulomb, right? Charge is expressed with a unit called Coulomb. Coulomb is nothing but joule per volt. So which means that you will have Newton volt by joule, which is nothing but Newton volt by Newton meter, and you will simply have volt per meter unit length, right? So this is nothing but volt per unit length. Okay. So this is also nothing but minus d psi by dx. So electric field can also be expressed as uh, you know negative potential. So gradient of, negative potential gradient, right? So here you will have the potential gradient, that is d psi by dx, okay, which is also nothing but volt per unit length. Psi is potential, potential is usually expressed as volt. So you get the same unit, right, as we just now obtained for Fc by Q, right. So here the sign negative indicates that the potential decreases as x increases, right. So this is nothing but a negative slope, okay, right. So now if you just simplify this, E is nothing but a slope here, and so what you will get is, let's say you will get psi, which is nothing but psi is equal to E into x plus c is what we get. If you apply the boundary condition that x is equal to 0, at x is equal to 0, psi is nothing but psi naught. Okay. So in such case, you will see that c is nothing but psi naught. So you will have, yeah, this is nothing but minus ex, right? Yeah. So you will have psi is expressed as psi naught, minus ex, right? Or you can say del psi is nothing but minus ex. Okay. So which means that psi is varying as a function of x, okay, as proposed by the Helmholtz, right? Yeah. So we'll stop here. We will continue from the next lecture. Thank you.